To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. In this lesson, I am going to discuss the PN junction with you all. So like I told you all, if we have an intrinsic semiconductor, that is a pure semiconductor like silicon or germanium, what we can do is we can dope it with another material. If it is group 3, we get the positive type or P-type semiconductor. If we dope it with group 5, we get the N-type or the negative type semiconductor. At the same time, now like I told you all, if we have a semiconductor, and what we can do is we can dope it with group 3 on one side, group 5 on the other side. So then what will happen? If we dope it with group 3, if it is going to be group 3, you get the P-type semiconductor here. At the same time, the other side, we dope it with group 5 elements. Group 5. So when you dope with group 5, we get the N-type. And this part, this thing is a PN junction. Now group 3, like a boron, they have only 3 electrons, whereas group 4 element silicon has 4 electrons. Because of that, there are additional holes in the P-type semiconductor. That is why we call it P-type or positive type semiconductor. Then on this side, we dope it with group 5. That has 5 valence electrons, which is 1 electron more than the silicon atom. Because of that, there will be free electrons. Therefore, it becomes a negative type semiconductor or N-type semiconductor. So, if we dope one semiconductor with both group 3 and group 5 on each end, we will get a junction where you have the P-type and N-type meeting each other. That is known as a PN junction. But this particular PN junction shows a specific behavior. That is what we will try to understand in this part of the lesson. So, if I read the note for you all, here you can see PN junction. By doping one side of an intrinsic semiconductor such as silicon or germanium with a group 3 element to form a P-type semiconductor and the other side with a group 5 element to form an N-type semiconductor, a PN junction can be formed at the center of the semiconductor. So here you all are familiar with all these words. Doping an intrinsic semiconductor such as silicon or germanium with group 3 element to form a P-type semiconductor and the other side with group 5 element to form an N-type semiconductor, a PN junction can be formed at the center of the semiconductor. Such a junction shows an electrical behavior that is different from the normal conductors. Now we will try to understand that. If we take this PN junction, now again this is the same semiconductor. We have a, so here also we have a semiconductor, and in this, now when we say this side is P-type, this side is N-type. In the P-type, what is the majority charge carriers? Those are the holes. So here we have holes. We have holes. And N-type, what is the majority charge carrier? Those are the electrons. Those are the electrons. Now here, at this situation, we have this PN junction. So there is a PN junction. Now in this, holes are positive charges, electrons are negative charges. You all know opposite charges attract each other. So what will happen is, some of these electrons will jump to this side. The electrons closer to the PN junction will jump to this side and they will fill up the holes. So what will happen? This side there will be additional electrons and this part will become electrically neutral. So the same conductor, that is the semiconductor PN junction, will become like this. If you look at it, once they form it like that, we will have holes here and the electrons have jumped to this point. So because of that, we will have electrons here. But this area where there were holes, it is neutral now. At the same time, because the electrons jumped from here to here, there is vacancy there. Vacancy for electrons. That also becomes a neutral region. So here there will be a region, this particular region, that becomes neutral. And that actually prevents the movement of these charges. Therefore, we call that as a depletion layer. Now, this is known as a depletion layer. Depletion layer. So, we had the doping process. So, we have the PN junction. P side you have the holes, N side you have the electrons. And what happens? The electrons jump from there to here and neutralize the holes. And here also there are no electrons. Because of that, there is this layer that is electrically neutral and that is known as a depletion layer. So this side we still have the P type, this side we still have the N type. Now this particular depletion layer does not allow the electrons to cross from here to here. The same way the holes cannot cross from here to here. Why? Because now here there were holes, positive charges. But the electrons moved here and combined with the holes. Now there is too much of electrons on this side. So, negative charge forms. Why? The electrons have moved here. And when the electrons went from here to here, there is a space created, no vacancy for electron. Because of that, this side becomes like a positive charge. So, the P type, this is P type, here also P type. P type is now connected. This is positive, is connected to negative there. And on this side, you can see N type, here also N type. That is the negative charge is now connected with positive charge there. So normally you all know when opposite charges are connected like that, this becomes a potential barrier. So this depletion layer becomes this particular layer. Prevents the flow of holes from here to here, electrons from here to there. So although we supply a potential difference, this region, the depletion region, acts as a potential barrier. Potential barrier. This is what we have explained in that. They say it shows a behavior, electrical behavior that is different from normal conductors because these are the extrinsic semiconductors. The semiconductors doped with group 3 and group 5. So can you all understand what happens here? I will explain the same process in the next slide also. So here you can look at the diagram. Here you can see, students, we have the p-type with the holes, n-type, the free electrons. So like I said, the electrons move from here to here, holes can also move. So that is what is shown as diffusion. That is the first diagram I explained to you all. As shown in figure A, as soon as the PN junction is formed, the free electrons in the N region diffuse across the junction towards the P region and the holes in the P region diffuse towards the N region. So that is something you have to remember. The PN junction is formed. The free electrons in the N region diffuses across the junction towards the P region and the holes in the P region diffuse towards the N region. Due to this diffusion, electrons and holes recombine, forming a region devoid of charges near the junction. So that is what I showed you all. This region is known as the depletion region or depletion layer. It is called the depletion layer or the depletion region. So that is something you all have to remember, students. So this is what happens as soon as the PN junction is formed. So in the next slide, we will continue the discussion. Here you can see. So after the diffusion from the P region, holes diffuse, N region electrons diffuse. So there is this depletion region or the depletion layer. This is also known as depletion layer. So like I told you all, because the electrons came here, there is an additional negative charge. This side, since there are holes, more holes in this region, it becomes positively charged there. So this is like being connected to the potential terminal like this. Negative terminal is connected to the positive p-type region. Positive terminal is connected to the N region. So because of that, that becomes a potential barrier. Is that clear to you all? So then, as shown in figure B, extra electrons have entered the P side of the depletion region, giving it a negative charge. So here you have to remember that. Extra electrons have entered the P side of the depletion region, giving it a negative charge. While extra holes have entered the N side of the depletion region, giving it a positive charge, generating a voltage difference across the junction. This potential difference repels the charge carriers, impeding the diffusion of charge carriers across the junction. So this particular potential barrier does not allow holes to go that side and electrons to come from there to here. They prevent the movement of charge carriers, that is holes and electrons, across the junction. So because of that, it becomes a potential barrier. Is that clear to you all? This potential difference repels the charge carriers, impeding the diffusion of charge carriers across the junction. So this is important. Therefore, this potential difference is known as a potential barrier. And this potential barrier is represented in the above figure as a hypothetical battery. That is why we use the negative and positive terminals as if they are connected in the opposite manner. P region of the semiconductor is connected to the negative terminal of the battery and the N region is connected to the positive terminal of the battery. So there is a potential barrier. And this potential barrier, the value depends on the type of the semiconductor. If it is a silicon semiconductor, then the potential barrier is 0.7 volts. And if that was a germanium semiconductor, the potential barrier will be 0.3 volts. You have to remember those values. Here you can see the magnitude of the potential barrier in a PN junction formed by silicon is about 0.7 volt. That formed by germanium is about 0.3 volts. Very important. You have to remember this. So, the magnitude of the potential barrier depends on the nature of the semiconductor. Potential barrier is 0.7 volts for silicon and 0.3 volts for germanium. So, to overcome this potential barrier, we have to supply a potential difference greater than this value. At the same time, we can do that in two ways. Now here, again if we take two semiconductors, here if we consider a PN junction, so this is P, this is N, this is the depletion layer, and here also this is P, this is N, this is the depletion layer. Depletion layer or the potential barrier. Now let's say this is a silicon PN junction with a silicon semiconductor, doping of group 3 and doping of group 5. So, we have a silicon PN junction. Now, we want to overcome this potential barrier. To do that, we need to supply a voltage greater than 0.7. Now, to do that, we can connect a battery, we can connect a power pack that provides greater than 0.7 volts. Now, we can do that in two ways. Let's look at that. Now, you can connect the batteries. I will leave space for the power source. Here you can see we can have the power source connected in two ways. Now here what I will do is I will connect the positive terminal of the battery with the P side here and the negative terminal to the N region. So this is positive, this is negative. P and positive are connected. The N side or the N region is connected to the N terminal of the battery. We can do it the other way, We can have the negative terminal on this side and the positive terminal on the other side. So, we can connect the negative terminal to this P region and the positive terminal to the N region. Both are possible. We can supply a voltage greater than 0.7 volts. That is also possible. If we do that, will current flow through the semiconductor in both instances? Will that happen? That is what we need to understand here. So, this process where we connect a potential difference, where we supply a potential difference across the PN junction is known as biasing. And there are two possible ways of biasing. And we will see whether they both conduct electricity or not, or whether only one type of connection will allow current to flow through. So this process where we supply a potential difference, that process is known as biasing. Biasing a PN junction. And the biasing can be done in two ways. I'm sure you all can understand that. We can connect the positive terminal to the P side and the negative terminal to the N region. The same way, we can connect the negative terminal of the power supply to the P side of the PN junction and the positive terminal of the power supply to the N region of the PN junction. So, we will try to understand that after this. So, then biasing a PN junction. That is what I told you all now. So, here applying a potential difference across the PN junction using an external electric source is known as biasing. So, what I explained to you all. Applying a potential difference across a PN junction using an external electric source is known as biasing. And depending on the direction of the bias voltage across the junction, it behaves in one of two ways. So, the two ways are, one is known as forward biasing . Biasing, that is when a current flows across the PN junction. And the second method is known as reverse biasing. That is when a current does not flow across the PN junction. So, that is, those are the two ways depending on the direction of the bias voltage, like I showed you all in this previous diagram. Here, the bias voltage is in this direction, positive to negative. Here, the bias voltage is in the opposite direction, positive to negative. So, based on that, one will allow the current to flow through, then we will call it as forward biasing. If the current does not flow across the PN junction, we will call it the reverse biasing. But either way, supplying this potential difference using an external power supply is known as biasing. Is that clear, student? So, here the two ways of biasing. With that, I am going to move on to the next slide. So, then we have an activity biasing a PN junction. To do this activity, these are the materials that are required to us. So, here we need a PN junction diode. PN junction, we need the PN junction because we are trying to observe the biasing of a PN junction. To get the PN junction, we have a PN junction diode. Now, there are different numbers to indicate different types of diodes. We choose one of those diodes as the PN junction diode. So, that will have the PN junction with the depletion layer in it. Then we need a bulb. A small bulb is more than enough because we just need to observe whether current is passing through the circuit or not. So, for that we need a bulb. Then we need batteries. We'll be using batteries as the potential difference or power supply to provide the potential difference. Then we need a switch. And then we need connecting wires connecting wires, and also we can use a circuit board. To get this circuit board, we can use a project board or a breadboard. So that is to connect the circuit. So these are the materials that we need, students. Here you can see, to observe the biasing of a PN junction, we need a PN junction diode, a bulb, batteries, switch, connecting wires, and to connect the circuit, we can use a project board or a breadboard. So those are the materials. I will move on to the next slide where I discuss the method with you all. This is the procedure. Now look at the two figures. Now here you can understand, this is the symbol for a PN junction. I will explain that to you all here. Here you can see, here we have this symbol. Now from here, the current flows in this direction. This side is positive, this side is negative. Current flows in that direction. This is a symbol for the diode. That is a PN junction diode. PN junction diode. So as example of a PN junction, we are using that, and this is the circuit symbol. So in this one, if you look at the two diagrams, now in this you can see the positive terminal of the battery is connected to the P region of the diode, PN junction. And the negative terminal of the PN junction is connected to the negative terminal of the battery there. So here of course we are using about 3 volt battery. So here we use a 3 volt battery. So you can see the connection. We have the batteries 3 volt. Positive terminal is connected to the P region of the PN junction diode. Then the negative terminal. Then we have the bulb there, so that we can observe whether current is flowing through the PN junction or not. Then you can see here it comes back, and this is the switch, and the switch is connected to the battery. Now here of course the switch is closed. On the other side, figure 2, you can see the terminals of the battery has been changed. Now here you can see the terminals have been changed. Earlier positive terminal, now it is the negative terminal. Same number of batteries, same batteries, only the terminals have been changed. So here the negative terminal is connected to the positive region of the PN junction diode, and here we have the negative region, then the bulb and the switch, and here the negative terminal is connected to the positive terminal. So the two types of connection. We are trying to understand biasing. We do it in both ways. In the first one, positive terminal of the power supply is connected to the P region of the PN junction diode. In the second one, negative terminal of the power supply is connected to the positive region of the PN junction diode. So both connections are used. Then, if you look at the procedure, connect the circuit on the circuit board. It can be a project board, a breadboard is better for this purpose. So you use a circuit board as shown in the figure 1. Turn on the switch and observe the bulb. Next, disconnect only the battery and reconnect the battery as shown in figure 2. So the same circuit, we only change the terminals of the battery. Turn on the switch again, observe the bulb. So in both instances, it is shown as the switch is turned on. we will see when the bulb lights. So that is the activity to understand the biasing of PN junction. Let's go to the lab and do this activity now. Okay students, so now I am going to do this activity in order to observe the biasing of PN junction diodes. So there are two types of biasing, the forward biasing and reverse biasing. So to observe that, I have all these materials. Here you can see this is a switch. I have connected two wires. Now I'll be using these two parts of the switch. So I have connected the wires here. You can see that now the switch is open. Now then I have dry cells, two dry cells. Now here you can see this is the positive terminal and the negative terminal of the dry cell. So I have to insert them into the case. So here already I have the negative, positive. So negative, positive. I have set it properly. Now we have 3 volt power supply or potential difference because of the two batteries is 3 volts. Then what I will do is I will connect the negative end with this blue color clip to the negative end of the battery. Switch is connected to the negative end, and then here I have the other connecting wire, the red color wire, to the positive end. Now that we have this, we need to have a diode, a PN junction diode. You all know the number IN4001. Here you can see this is a diode. Now there are two terminals. We need to identify the terminals. Now if you look closely here, there is a silver color or white color line there. Here of course it is a silver color line. Normally there will be a silver color or white color line there. So normally in a diode the current has to flow in one direction. That is what we need to identify now. So here also I have connected the diode in this circuit board. We are supposed to make the circuit board where we have the silver color line on this side. This side towards the bulb is the silver color line. Here you will be able to see it's a faint color, but you can, if you look closely, you will see there's a silver color line towards the bulb side. So here this is the brown color wire and the blue color wire. So we have the conducting wire, then the diode connected to the bulb, and there is a continuous connection. If you look at it, everything is a complete circuit there once we connect these conducting wire. So what I will do is I will connect this to the brown color terminal and this to the blue color terminal. Okay, so now I have connected the circuit. You all can see students, I have two batteries, so there is a potential difference of 3 volts provided to the circuit. So then I have the switch here. Then the conducting wires are connected. So starting from the batteries, the potential difference is supplied. Then here you can see this is the diode. Now if you look at the diode, now I have for you all to understand, I have this diagram also. This is how we have connected the diode. Now if this is the symbol for the diode, this is the P terminal, that is the N terminal. So now the P terminal has been connected to the positive terminal of the battery, and on the other side N terminal to the negative terminal of the battery. This is how it is connected in this direction. Now the switch is open now. If I close the switch, you all have to observe what will happen. Now when I close the switch, that means it's on. Look at the light bulb. You can see it light. So that means there is current flowing through the diode. If current flows through the diode, we say that the diode is forward biased. So now if I open the switch, bulb does not light because there is no current flow. When I close the switch or on the switch, you can see the bulb light. So there is current flowing through the diode, and the diode is said to be forward biased. So you have to remember here the positive terminal of the battery is connected to the P terminal of the diode, that is this terminal of the diode, and the negative terminal of the battery is connected to the N terminal, that is this side of the diode. And also if you look at the physical appearance, the silver color line is towards the N terminal of the diode. So now I'll open the switch. Now what do we need to do? We need to change the terminals of the battery. So I'll remove the clips and then I will switch the batteries. Now you all know this side is the negative terminal. Here you can see this is the negative terminal. This is the positive terminal. I have changed the terminals of the battery. So now what I am going to do is I am going to connect the negative terminal of the battery to the P terminal of the diode. Negative terminal of the battery to the P terminal of the diode and the positive terminal of the battery to the N terminal of the diode. So still the diode is this way, but now negative terminal of the battery has been connected here, positive terminal of the battery has been connected there. Again, if I on the switch, look at the bulb. Do you see any difference? No, the bulb does not light. Now the switch is closed. That means current has to flow, but there is no current flow. Why? The bulb does not light. That is because the diode does not allow current to flow in the opposite direction. That is, if you connect the negative terminal of the battery to the P terminal of the diode, then there is no current flow through the diode. That is why the bulb does not light. So this type of biasing is known as reverse biasing. And when the diode is reverse biased, current does not flow through the diode. So from these activity, students, you all have to understand when we use a PN junction diode, we have to connect the positive terminal of the battery to the P terminal of the diode and the negative terminal of the battery to the N terminal of the diode. Then it allows current to flow through it, and that is known as forward biasing. If you connect the negative terminal of the battery to the P terminal of the diode, then there is no current flow through the diode, and that is known as reverse biasing. Okay, students. So did you all see what happened during the activity? I am sure you all observed the changes. So when we connected the circuit this way, when we had the positive terminal connected to the P terminal of the PN junction diode, you were able to see that the bulb lights. So in this one, bulb lights. But when we switched off that circuit, then we changed the terminal as shown in figure 2, and then again when we switched on the switch, closed the switch, the bulb did not light. So here bulb did not light. Bulb did not light. Now what does that show us? Here the bulb lights. That means there is current flowing through this circuit. So here there is current flow. But here there is no current flow through this circuit. So here bulb did not light. There is no current flow. So what happens? When you connect the positive terminal of the battery or the power supply to the P side of the PN junction diode, it allows current to flow through it. And that type of connection is known as forward biasing. This is known as forward biasing. Here, when the negative terminal is connected to the P side and the positive terminal is connected to the N side, there is no current flow, and that type of biasing is known as reverse biasing. Reverse biasing. So only when the diode or the PN junction is forward biased, it will allow the current to flow through it. If it is reverse biased, it will not allow the current to flow through it. So here positive terminal connected to the P side of the P region of the PN junction. Then there is current flow, that is why you see the bulb light, and that means it is forward biased, or that type of biasing is known as forward biasing. Forward biasing of a PN junction allows the current to flow through it. But on this side, in figure 2, we have the reverse biasing. Reverse biasing means connecting the negative terminal to the P region of the PN junction. There is no current flow. That is why we did not see the bulb light. And that is known as reverse biasing. Now we will try to understand what this forward biasing and reverse biasing are. So here, if we try to understand that, if we take this PN junction, on both sides I will take the PN junction. I will draw the diagram and then I will explain it to you all. So here we already have a depletion layer. Positive, negative, positive, negative. So then this side is P, this side is N. This is P, this is N. Now, in the P side we have holes and N side we have electrons. Now, when you have the N terminal connected to the N terminal, or the N region is connected to the N terminal of the battery, now this N terminal of the battery has the ability to repel electrons. So, what will happen? Now, this will try to push the electrons. The negative terminal will try to push the electrons. Because of that, the electrons will flow through this and they will come into this N region, and there they will try to push the electrons towards the depletion layer. At the same time, now the positive terminals are here, the holes are here, both are positive. So because of that, due to the positive potential provided here, the holes will be pushed this way. So holes will move towards the depletion region. The same time, electrons also move towards the depletion region. Because of that, the depletion region will become smaller and smaller. So here, this region will become smaller. This becomes smaller. And at one point, when it is a silicon semiconductor, if the potential difference is greater than 0.7, at that point, there will be no depletion region. And at that instance, current will start flowing through the circuit. And that is known as forward biasing. So, this is forward biasing. On the other hand, when you connect the PN junction this way, now here also we have the P region and the N region. Now P region we have the positive terminal, positive holes, and N region we have the negative electrons. Now how have we connected? The positive terminal is connected to the N region. N region is negative electrons. this is the positive terminal. Then what will happen? The electrons will start flowing from the end region towards the positive terminal. They get attracted to the positive terminal. Because of that, electrons will start moving this way. So what will happen is, here will be moving out of the end region. So these electrons are moving out of the end region. So what happens here? The depletion region becomes larger. At the same time, this is the negative terminal, these are the holes. Electrons will get attracted to the holes, they will move towards the P region and they will fill up these holes there. So because of that, this side also the depletion region will widen. Now what has happened? The depletion region has become more broader. So depletion region becomes more broader. So more broader means what happens to the potential barrier? Potential barrier increases further. Then will that allow the charge carriers to flow through? No. So then there will be no current flowing across the PN junction. So this type of biasing is what we call as reverse biasing. Reverse biasing. So when a PN junction is forward biased, it allows current to flow. So forward biasing, current flows. Reverse biasing, there is no current flow. So only when the PN junction is connected in one method, positive terminal of the power supply to the P region of the PN junction, then there will be current flowing across the junction. Otherwise, there will be no current flow across the junction. Is that clear to you? So this will help us to use these PN junctions in certain circuits. We will try to understand that after this discussion. So with these students, I'll move on to the next slide where I will discuss the same biasing procedure again with you. So before that, we have an extra knowledge slide. So in order for the PN junction to be forward biased and allow a current to pass through it, a positive potential should be connected to the anode and the potential difference applied should be sufficient to overcome the potential barrier across the junction. So for silicon diodes, this value should be greater than 0.7 volts and for germanium diodes greater than 0.3 volts. So this is what we discussed before. Here you can see, in order for the PN junction to be forward biased and allow a current to pass through it, a positive potential should be connected to the anode and the potential difference applied should be sufficient to overcome the potential barrier. So we have already discussed for silicon it is 0.7 and for germanium it is 0.3 volts. So that is what we discussed before. Forward biasing a PN junction. Is that clear, student? So when you forward bias the PN junction, the depletion region becomes smaller and smaller, and at one point there will be no depletion region. And thereafter, the holes and electrons, the charge carriers, will flow across the PN junction. That is when the PN junction conducts electricity. For that to happen, it should be forward biased and also a potential difference that is enough to overcome the potential barrier should be supplied. I'm sure you all can understand that clearly. Okay, students. So with this, I'm going to end this chapter, and in the next chapter, when I start the chapter, I will again discuss with you all the process of forward biasing and reverse biasing and what happens to the depletion layer when we do that, and why forward biasing allows current to flow through it and why reverse biasing does not allow current to flow through it. I have already discussed this with you all. I have explained the process to you all. Again, when we start the next chapter also, I will discuss that with you.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.